Good afternoon, everyone. My name is Nathaniel Scott, and today I'm going to be talking to you about torque wrenches. So a little bit before we begin, let's go ahead and just get started off with the agenda. In my presentation today, I'm going to cover what is torque, the different types of torque wrenches that there are, proper torquing techniques, the importance of torque values, and the use of torque extensions. So the big overall question is, what is torque? Well, torque is defined as a twisting motion that tends to cause rotation. If any of you understand how an engine works, you'll know that as the gasoline burns inside of the cylinder, it pushes down on the piston, which causes rotation in the crankshaft, which is then translated through a series of gears into your wheels. It's much like pedaling a bike, if you've ever done so. When you move your legs up and down, you twist the crank, which moves the chain, which then moves your bike. Or if you've ever used a screwdriver, you insert it into the screw and apply a twisting motion with your wrist. This rotational force that we're talking about is what's known as torque. Now, torque can be measured in several different units, such as inch-pounds, foot-pounds, and the Newton meter. But we're going to focus on inch-pounds as it's the most common. So with our different types of torque wrenches, we've got three main ones. We've got a click type, a beam type, and a dial type. Now with a click type, there's a vernier scale on the side and a threaded collar that you use to screw up to the value that you want to input on this torque wrench. Now as you apply the torque using the wrench, it actually has a spring in here that's calibrated to match that vernier scale to whatever input you set it as, be it 55, 60 inch-pounds, really whatever you want. When you finally reach that torque value after cranking with the click type wrench, the head will bend slightly from the shaft. It's very subtle, but you'll hear a small click, and that'll indicate that you've reached your desired value. Now the next type of torque wrench is the beam type. This torque wrench has a scale along the side of the wrench, along with the bar that goes down the middle. As you continue to rotate the head of the torque wrench to achieve the desired value, the pointer will begin to move along the scale, indicating how high or low you are. So if you want to say, hey, I want to put 60 inch-pounds, you crank it over to 6. And our final type is the dial type. Now this is what we'll focus on. The dial type actually has a dial on the face of the torque wrench that gives you an output of how many inch-pounds you're putting into the bolt. This is the easiest to use and the most common. So, correct torque values. Why are they actually so serious? Why do we need to pay attention to them? Well, the biggest reason is that we need to have a secure fit on all the parts that we're installing. Our parts need to stay attached. Here's a picture of a DC-10 that crashed due to incorrect torquing values. On May 25th, 1979, American Airlines Flight 191 crashed when it was taking off from O'Hare in Chicago, Illinois. A DC-10 technician had incorrectly installed the engine pylon, and as the plane rotated for takeoff, the number 1 engine, which is on the left side of the aircraft, actually tore off and shot up and over the wing. This accident killed all 271 passengers and crew and killed an additional 2 people on the ground. As you can see, inputting the correct torque values is very important to avoid accidents. Another reason that we need to use correct torque values is to avoid overstretching bolts. The top bolt you can see is of normal length. There's no defects in it. All the threads are at a normal pitch and distance. This bottom bolt, however, you can see is over torqued. The shaft of the bolt narrows down where force was applied at the surface that the bolt was attached to and the threads where it was actually engaging. The bottom bolt's been over torqued and has actually caused that bolt to pull and stretch further than it was intended to. So you may be asking yourself, where am I actually going to get these values from? Well, it's fine and dandy that I need to put a torque value on, but where am I actually going to find that? As a worker in a factory, on an assembly line, or even as an auto mechanic, you'll most likely be given the torque value needed in work instructions. However, that won't always be the case. You may be able to find these torque values in a maintenance manual, an owner's manual, or a torque chart. Now here's where I need to make an important point to you. When you're measuring bolts, you need to be careful where you're actually taking the measurement from to determine your torque value. As you can see here, the head of this bolt is much larger than the threads. If I say that the head of this bolt is, say, half an inch, and perhaps the threads are 1/4 of an inch, if I go to the torque chart and look up the torque value for half an inch, I'm going to over torque this bolt and cause stretching in the threads, which might cause the bolt to fail. Because the head's diameter is so much greater than the thread diameter, you'll put on too much torque. So when you're measuring out this bolt to determine the amount of torque that you're going to apply, always make sure that you actually measure the threads themselves, not the head of the bolt. So now let's go ahead and look at proper torquing techniques. This diagram should look familiar to any of you who have ever had to replace a tire on your car, change a flat, that sort of a thing. What we have right here is a diagram of wheel wells. Now I decided to choose this because I figured that this would be what most people would have experience with and would make the most sense to someone. Now if you've ever been taught how to actually change a wheel on your tire, you'll know that you don't follow a pattern starting with 1 and then moving horizontally or vertically across the wheel as you tighten down the bolts. What you're actually going to do is you're going to follow a diagonal pattern as you torque the bolt, starting here, moving diagonally down to 2, moving up across the face of the wheel to 3, and then finally back down to 4. It's the same thing for a 5 bolt and a 6 bolt system. Most cars usually employ 6 or 5 bolts. You'll start with 1 bolt. Now it doesn't really matter where you start. For the purposes of this diagram, we're just going to start up here. You'll move diagonally across the face of the wheel and continue this pattern, never moving to the next bolt adjacent to it, but actually moving diagonally across the face of the bolt, unless of course you're on a 4 bolt where you don't have that option. But as you move, you want to continuously move across diagonally until you've tightened down all the bolts. Now the reason that we do this is because if I start here and input my torque value and move this bolt, all of a sudden I'm going to have a lot of stress up here in the face of the wheel. If I move down to the second bolt, that stress is going to continue to distribute and be created along the edge. What might actually happen is because I'm torquing just on one side of the face, I may actually bend and warp the metal around the wheel, which is something that we want to avoid. Another important point to make is that when we torque and run through these patterns, we always run every bolt up half of the torque value. So we'll start with 1, run it to half, 2 to half, 3 to half, 4 to half, 5 to half, and then repeat the pattern, running it up to the full torque value, 1, 2, 3, 4, and 5. For example, if I wanted to put on 60 inch-pounds of torque, I'd do 30 inch-pounds, 30 inch-pounds, 30 inch-pounds, 30 inch-pounds, and then finally 30 inch-pounds. And then I would repeat the entire pattern, but add the additional 30 inch-pounds on each individual bolt to run it up to 60. So some things that we want to keep in mind while we're applying the torque is normalizing torque, running torque, and wet versus dry torque. Now what normalizing torque means is when I input the torque value onto a bolt, I'll hold for 10 seconds. The nut will actually continue to rotate around the bolt during these 10 seconds, and this extra time allows us to ensure that we've input the correct torque value. Now running torque can be thought as friction. It may have to be added to a torque value, but it'll depend on the application and your instruction. As you twist on a nut, it'll incur resistance against the bolt and may actually increase the amount of torque that you have to input to make sure that you've got the correct value on there. Now wet versus dry torque. These are for specialized applications. Most bolts will utilize a dry torque value, but depending on the application, you may have a wet lubricant such as oil on the nut that will require you to use a different torque value. Consult all your instructions and manuals before you begin. So now that we understand what torque is and how we apply it, let's move on to extensions. There may come a point in time when you're trying to apply a torque value to a bolt and it's just not possible to get the torque wrench around or into the space that you actually need to work with. When you run into a situation like this, what you'll use is a torque wrench extension, such as the one pictured here. Now what this diagram shows is a torque wrench with the extension and the mathematical formula that you'll use in order to actually calculate what difference this extension length makes. Now let's run through all of the variables here real quick so you understand what we're actually looking at. L stands for the length of our torque wrench, which is measured from the center line of the torque wrench socket to actually, this is incorrect, it should be on the end. The very end of the torque wrench is where we take our length from. Now, TA is the actual torque, which is the actual input that's going to be twisted onto the bolt using this apparatus. TI is the indicated torque value, which is what will appear on your torque wrench dial right here. A is the extension length that's measured from the socket of the extension to the socket of the torque wrench. Now it's very important here that when you make this measurement, you measure the lateral distance between these two sockets, not the actual length of the extension itself. Again, very important. When you take it, make sure that you're measuring from the centers of these sockets the distance laterally between them. The reason that this is important, and the reason that we have a plus and minus right here in our formula, is that this extension can be moved in a full 360-degree range of motion to any angle that you want. Now, the distance that this lever takes up is relative to the position of the socket, so its effective distance will change. Now if you have the extension out in front of the torque wrench like it's pictured here, you'll have a positive extension, which means that you'll use the plus sign in this formula. But if we were to take this extension and move it back behind the center line of the socket, we're actually effectively shortening this entire wrench. Therefore you'll use the negative symbol. It's very important that you pay attention to which side of the socket you have this wrench on and that you use the correct mathematical formula. So now let's go ahead and run through an example problem. If I gave you a 1/2 inch diameter bolt that was required to have 22 inch-pounds of torque applied, but upon attempted installation you discovered that you needed to use a +3 extension in order to reach the bolt, what would you actually do? You've got a 12-inch torque wrench, so what indicated value should you torque the bolt to? So using the torque wrench diagram that we've seen before in our mathematical formula, we will now solve this problem. The first step is to fill in all of the variables that you know. You know that you want to apply an actual torque value of 22 inch-pounds to this bolt. You also know that your extension length is going to be +3 inches, keeping in mind that that's measured laterally from the center of the extension socket to the center of the wrench socket. And you know that the length of the actual wrench is 12 inches. The indicated value is your variable in this problem. So with all of this information, plug it into the mathematical formula and this becomes our solution. We have 22 inch-pounds, which was our actual desired torque, multiplied by the length of the wrench, 12 inches, divided by the length of the wrench, 12 inches, plus 3 inches, since this is a positive extension, which will equal our indicated torque. Use simple algebra to solve and simplify this problem, and you'll find that you'll need an indicated torque value of 17.6 inch-pounds. And that's all there is to it. Thank you for watching this video, and I hope that you found it very informative and helpful. If you wish, go back to the beginning and review the video just to make sure that you have all the steps down. If you feel confident in your ability, now it's time to move on and attempt the torque wrench practice assignment.